Brilliant. Okay, so we're now going to hear about JPMatch, which is a nice play on JPM. So over to you, Antigoni, about stock trading. Thank you.
Thanks a lot, Nigel. So I'm going to talk actually about privacy-preserving auctions. And this is actually joint work with Tucker, Manuela, Ben, Hans, Gabriele, and Richard. So as you know, I joined JP Morgan 1.5 years ago. I keep doing my research, but actually what is nice, we found some applications in the real world, and I have these amazing new collaborators to help push this through. And I'm going to present you with the problem of axe matching. Okay, so axe matching is a term which is used internally in JP Morgan. And this is a service that is provided from different banks, not only from JP Morgan. So I'm going to jump directly to the problem and tell you what's the current state of this axe matching. And then I'm going to tell you what are some issues with the current process and how we can solve them using actually secure multi-part computation. And please feel free to stop me whenever you want if you don't understand anything, okay? So today what's happening, so we have in the bank our inventory, and what happens, so every day we send a list of our inventory to particular clients. It's usually actually 60 to 80 clients, okay? We send this daily, usually through email. Then the clients look at this list, and if there's something that they're interested in, they come back to JP Morgan, and we're trying actually to match these trades and execute the trades, okay? Here is an example of what is this axe list. So it's the usual thing. So you have like a symbol, like the stock, and then the side, if you want to buy or sell, or long or short, is the same thing. And then how many shares you want to get from this particular stock, okay? And here is a current issue. So this is JP Morgan's inventory, okay? And how we created this inventory. So let's say yesterday we executed some trades with our clients. So now our inventory changed, okay? So basically, if you think about it, this inventory includes inventory that we have from the interaction with the clients, okay? So let's say that we did something with a client yesterday, today it might be reflected in the inventory. However, some clients that they are big players of some stocks, let's say they hold most of the stock, there is some concerns, oh, I don't know what's that, sorry. There is some concerns that the inventory reveals their trading activity that they did with us, okay? And this is not desirable. And even some clients ask to have their positions removed from this axe list. And this, what this means is that now our inventory is reduced, so we have something that we cannot offer, okay? And this can have like some consequences in the P&L, which is actually profit and losses, okay? So this is the issue that we start with. Okay, do you have any question about the problem? Everything clear? Okay, I assume yes. So we're going to solve this problem based on I split them in 4 different categories. Okay, so, and we're going to use techniques from differential privacy and multi-party computation. Okay, so here, this is the names that we give them. And I'm gonna go over them one by one. I will focus more on the auction part, which is actually the two-part inventory matching and the multi-part inventory matching. And actually, these applications are going to production. The first one is going to production actually this month, and the other ones at the end of this year. So I'm gonna tell you more details about that. So let me start quickly about the differential private inventory obfuscation. So this is just to enhance the current process, okay? So I told you what's the process. We are sending them a list today. They look at the list, they come back to us and tell us what they want to do. And as I said, some clients raise concerns about having their positions in their list. Okay, and for that, we're going actually to use differential privacy to obfuscate this list. And this is to improve the current process. And then we have these enhancements on how we can also actually ask also the clients to send us what orders they want to have and then try to match. So I will go over them and I will define the problems clearly. So in the first one, as I said, so what we're going to do, we're going to use differential privacy to actually mask our axe list, add noise. But we want to add noise based on a measurement, based on some measure, right? And the measure here is this P&L. because we don't want to actually add too much noise. And let's say a client wants to buy some stock, and we saw, because we added noise, that we have a lot of this stock, okay? And then the client wants to buy that, and then when he comes back to us, we say, oh, actually, we don't have it. Actually, we need to go and find it. So we don't want to get a lot of risk. So we want to add as much noise as possible to hide the client positions, and at the same time, preserve the P&L, okay? And what will be the goal out of this process? So basically, whether the client positions will be in this X list or they are not, then we shouldn't leak any information about this individual client. And the client better keep his positions inside the inventory. Okay, so here is the problem. So we have the two inventories. Okay, so let's say this is like the first list with all the positions of all the clients. This is the second list with, again, all the positions of the clients. But let's say in the second one, we are removing the second client. Okay, and here the problem is when, as I said before, a client holds a large position of this particular stock. So let's say client 2, let's say that was the Apple stock, and the client was having like most of the shares of the Apple stock. Okay, so now what we want to say is that looking at these two lists, so whether the client's positions are included in the list or not should be statistically indistinguishable from the other set. Okay, so these two sets should be statistically indistinguishable, and I want to say here what we are hiding. Okay, so here we are hiding the changes in the client's positions from day to day. For example, let's say if yesterday he was going long, okay, he wanted to buy a stock, okay, and if today he's going short, okay, we don't want to actually reveal what he's doing every day. So let's say yesterday he was going long, today he's going short, then we don't want to reveal that today he's going short, okay? We are trying to hide the direction of the changes, okay? And you all know what's differential privacy. Super quick, I'm going to define it here. So we say that the mechanism is epsilon differential private if we have like two neighboring sets, X and Y, differing in one element. So here it will be in the data of a single client. Then the probability that some bad event happens when we are working with the dataset X is almost the same as when we're working with the dataset Y, up to this factor epsilon. And if I rewrite this, so the smaller the epsilon, the closer the probability, so we have more privacy, okay? And the bigger the epsilon, we are more accurate but less private. So everything depends on this parameter epsilon. Okay, and there's this trade-off between the epsilon, and in our application will be the P&L, okay? So as I said, we cannot add too much noise and have like a negative P&L. And with differential privacies, we know we are not hiding all the information about the data set. We are hiding only particular information, okay? For example, here we're hiding the nationality of the guy that is talking. In our case, what we're going to hide is whether one client's positions are in the inventory list or not, okay? This is what we're trying to hide. We're not trying to hide generic information about the inventory. When we do the auctions, we will actually hide completely everything. I will come to that. Okay, so as I said, we need to find the right trade-off between the epsilon and the privacy. The epsilon and the P&L. Okay, and here is the challenge that we have. So this is not a static data set, okay? So as I said, we are publishing this inventory every day. So it's not that we have the data set, we add the noise, and then we are done, okay? So the adversary can look at the data set every day. So we need differential privacy under continual observation. So that was the technical challenge of this work. And there are actually some works in the past from Dwork et al. And Chan et al. Where they did differential privacy under continual observation, but they did it like for simpler functions. It was actually a count function where actually you have streaming data that they are 0 and 1, and you want to count actually how many zeros and ones you have. So they did it for this type of functionalities. Here we had another functionality, right? So here we need to actually publish from day to day how the X changes. So we had actually we are based on their work, and we had actually to introduce some new ideas to make it work for our functionality. So if you're interested in that, contact me and I will let you know about the algorithm, and it will also be public. So I'm not going to talk about this algorithm. I will focus more on the secure multi-party computation, but I'm going to show you actually the results on when we run actually our new algorithm on a real data set, historical real data sets for different values of epsilon. Okay, so here, what are these histograms? So first of all, we have actually in the first row, we have what's happening in 1 day. Second is 7-day lag. So when we keep publishing the data set for 7 days, and then the last row is for 14 days. Okay. So in the first one, so this is a histogram of the stocks. Okay. So here you can see how many stocks, and here we're defining what we call leakage probability. So what is this leakage probability? I told you before that we want to hide whether a client is going long or short, the changes in his positions. Okay. So this leakage probability is actually half if we are not sure how he changes the direction. Okay. If it is more than 0.5, then we can actually guess correctly how he changed his direction. And if it is less than 0.5, actually we are guessing incorrectly. So the closer that we are to 0.5, the better. So in the first column, we have actually our differential private obfuscation with the client positions inside. And in the second column, we still have, again, obfuscation, but without these particular client positions. And here we're comparing what is the difference, okay? And this is for 0.9. Okay, and as you can imagine, like the bigger the epsilon, actually the less privacy we have. So now for 0.5, you see that these probabilities are coming closer. And for example, for 0.1, you see that they're almost very close to each other. So what this tells us, so whether the client has the positions inside our inventory list or not, then the probabilities are the same. So you see here that the client better keep his positions inside. Okay. So that was a quick introduction to what we are doing actually now. And this is what is going to go live in production this month. And this is to enhance the current process, okay? So now when we move to the auctions, actually, sorry, I had some examples to show you here how the differential privacy looks like. Sorry, let me go over it quickly. So here you can see that the blue one is actually, this is for a particular stock. The blue one is actually how much we have based on data for 1 year. This is the true value of the inventory. Then the green one is the client positions. Remember that I told you that the client holds a lot of positions in this particular stock. That's why it's actually very close to the blue one. And the orange one is basically what we are going to publish. Okay, so that's an example to show you how it looks like. Okay, and here I have some graphs showing that the P&L does not change. So here we have actually, again, it's a histogram of the number of stocks. And here is how much money we are losing or gaining for these particular stocks. So here is the difference between the P&L when we do the obfuscation and when actually we don't do the obfuscation and we exclude the client. And here is actually when we do the obfuscation, including the client, and the obfuscation when we exclude the client. So you see that the P&L in these two cases is very similar. So we are able to achieve the same P&L as we do today, where we're not hiding the client positions, and at the same time actually hide the client positions if we include them. Okay, so now let's go to what I was saying before. So the first application was to improve the current process. And when we want to do the secure auctions, we cannot change the current process. We cannot jump from one to the other immediately, right? Because as I said, also other banks are doing this. So if we stop sending our inventory, the clients will go to the other banks and get the inventory from there, okay? So we had to think how we can do these particular auctions here. And in fact, you know, they're not building anything if you do not get the feedback from the clients before you start building anything. So I had the chance to actually go and meet the clients and see what are their needs and what they would like to see. And we got feedback from 20 clients. So whatever I'm going to say here and the setting, the MPC setting that I'm going to define is based on the feedback that we got from these clients. Okay, so let's move to the two-party case. So the problem is the same, okay? We have the JPMorgan sending the inventory. So another issue that I did not mention, which actually you can guess, is that from this process, also JPMorgan is revealing its own inventory, okay? So we are also revealing our inventory. And moreover, there are some regulations and firm restrictions that does not let JPMorgan reveal or include in this inventory our full inventory, okay? It's some filter inventory. We cannot put our exact inventory today when we send the list out, okay? So first we had the problem that the clients were complaining that their trading activity is being revealed. Then we are revealing the inventory of JPMorgan, and moreover, we are revealing the inventory, but we cannot actually make available our whole inventory because it's filtered. Okay, so what we can do, as you can guess, so let's do two-party computation. So instead of sending the DAX list to the client, we're actually going to have JPMorgan and the client run a two-party computation, okay? Here, there's a change in the process, okay? So the client now is asked to send what he wants to do encrypted, okay? In the previous process that I told you, the one that we're using currently, client does not send anything. He just receives from JPMorgan, and then he thinks of what he can actually do. Okay, so there's a change in the process here. That's why client feedback is important. Okay, and the solution is, okay, let's use two-party computation and have the client submit his list in some encrypted way. And then what's the benefit? So we can actually offer the full inventory of JPMorgan and have like more specialized matches, okay? So this is the two-party case. And actually the two-party case, it was very easy to instantiate, is in the following sense. So if you think about it, okay, so we have the two parties. Let's focus on one symbol, okay? So what do you need to compute? You basically need to compute the mean of the two values, okay? The two quantities. And I have to say that it's not, we can also accommodate partial matches, okay? So if JPMorgan has 10 shares of Apple and the client wants 5, we'll give him 5. It doesn't have to be like an exact match. Okay, and this is why we need to do a comparison. So to do that, we are using the malicious garbling of Wang et al. And so when the client wants to do transactions with JPMorgan, he comes and then we just invoke the two-party garbling. And then at the end, we're finding out what are the matches, okay? And I can give you some benchmarks. So this is actually fast. So we can do, I lost the benchmark. Oh yeah, for 256 symbols in one garble circuit, actually it can take 0.49 seconds, okay? So this is like a solution that we have for the two-party matching. Okay, let's move to the multi-party X matching now. So here, what is the new property that we are adding? So what I said so far, so okay, so now with the two-party case, we can hide JPMorgan's inventory. We can offer the full inventory. Then we don't have the clients raising these concerns that trading activity is being revealed. And also now what we can do, let's try to see if we can match clients together. So let's say a client asks for something that we don't have, but maybe the other client asks the opposite, okay? So this is what the multi-party is going to do. So we can actually start matching clients and achieve better internalization and offer actually even better rates. Okay. So here is actually our requirements for the problem. So, and this is based on the feedback we've got from the clients and of course from JPMorgan. Okay, so we should not have communication between the clients no matter what. Okay? So the topology should be a star network. Then the clients, so these auctions that I told you, they're actually non-continuous auctions. There's this dark pool that is continuous, but the ones that I'm talking about now, they're non-continuous, and actually they require that the clients that they want to participate, they will come in the morning, some fixed time. They will commit to whatever they want to trade, and then the matching will start, okay? So all the clients must commit to what they want to do. all of them until, let's say, 8 a.m., okay? And this is actually a restriction, and you will see why, like they need to commit, and then in secure computation, actually, we need to make sure that they're using the same input that they use when they committed. So it creates some issues. Also, we want to support partial matches, and the client computation should be actually minimal. We should not use the client to do all the matches, okay? So if we have like, I don't know, 100 clients, we should not use the computation of all the clients to do all these matches. Then we really need malicious security. We cannot go with covert security or semi-honest. Like if you go to covert, you don't want to start disputes with banks. And then we also want to have a fair solution. For example, you want to say like first come, first served for the clients, whoever like places the order first till 8 a.m. So it must be some ranking. Or you can use some other model, okay? So you should not have some preference over some clients. So this is the model that we have, and we had to devise a solution for this particular model. Okay, and actually we do have the solution, and this is the application that will go in production at the end of this year. And actually I have to mention here, actually Nigel had the work that they did this kind of auction. They call it volume matching. It's the same thing here. We're trying to match the quantities. The price is fixed, okay? However, their topology was not a star network. They had like more servers in the middle, okay? So this does not accommodate our needs here. So let me show you the semi-honest version, but I will only present the idea, and then I'll tell you what are the challenges for malicious. So here is a semi-honest greedy approach.
We've got about a minute.
Oh, but I started a bit.
Yeah, okay. We'll give you 2 or 3 minutes, but just give you an idea, okay?
Okay, good. Okay, so I'm going to show you the semi-honest greedy approach. So let's say we have 3 clients and we want to match them together, okay? So the first one wants to buy Apple, the other 2 want to actually sell, and we can actually give 75% for the long and 100 for the short. So the first step is that the client somehow encrypt the orders, they send them to JPMorgan, and we do a secure aggregation, okay? And then we know how much short and how much long we have to offer. Okay, and then what we do, we go to every client one by one, let's say first come, first served, and we see how much we have available, and we compute actually a secure mean to find out how much we can match, okay? So the first one we can do like 120, the second 50, and the fourth 70, okay? And now, the first proof of concept that we have, actually it was also with Gilad, who was in JPMorgan, how we did it. So for the secure aggregation, we used the Diffie-Hellman exchange to do that. And then for the mean, we again used Garbling. So there are multiple issues here to make it maliciously secure, because you have these 2 phases and you need to make sure that the parties are using the same input in both phases, okay? So you can do it, but it will be very expensive. And another thing that you can do, so let's use the secure Garbling that we showed before, and let's make the simple thing. Parties commit to their inputs before the process starts, and I told you this is a requirement. And then we start running 2-party mean between the clients, okay? But if we start doing that, we need to make sure that the parties use the same input in the Garbling, okay? That means that we need actually to have a check inside the Garbling that takes the commitment. And this is not ideal, okay? Garble circuits are good for Boolean, so this will not be very efficient. Okay, and very quickly here, I'm gonna tell you how we are doing that. So basically, we're trying to find a more efficient solution. And this efficient solution, we're going to use actually secret sharing. And what we're going to do, the parties actually will commit to their inputs at the beginning of the protocol. And here they will commit to shares. And when I say here 3-party, I don't really mean all the parties have the same roles. 3 parties that only the 2 parties have inputs, okay? The 2 parties that we want to match, and JPMorgan is the 3rd client, okay? JPMorgan does not have an input. That's what I call 3-party computation here, just to be specific. Okay, so everybody commits to the shares, and then we're computing 2-party mean for the 2 quantities through the bank. And remember what I told you, the 2 parties should not communicate with each other. Everything should happen through JPMorgan, okay? And here I wanted to show you the semi-honest version. It seems that I don't have time, but I'll tell you that compared to previous works, what we did here, so, and this can be of independent interest, so we were able to have a 3-party comparison protocol where again, the two parties only provide input. And we're able to do that without requiring any multiplication. And the protocol is just one round, okay? So it seems I don't have time to show you that. Okay, and then as a last thing, I had just a pointer to the dark pool. So everything that I showed you here was a non-continuous auction with a fixed price, both the two-party and the multi-party. So in the dark pool, basically you also have a price, okay? So it's the same problem, but you also have a price. And then what you do, so a new order comes and you're trying to match, for example, this is a sell. So you go, and this is sorted, okay? So you also have things sorted, which is not very computationally efficient. And you're going over the clients and you're trying to find what orders you can match, okay? And we also have a solution actually for the dark pool. And for this one, we are using actually a GPU implementation of an FHE library, and we even optimized it further. And what we can currently do, we can actually do 512 orders in this start topology, okay? We really cannot avoid the start topology. So 512 orders in 11 seconds, okay? And we have a new secure implementation of a priority queue where actually we don't need to go over all the orders to find matches and compare the prices. Okay, so just to conclude, so I showed you this X matching problem that we have in JP Morgan, and we have solutions to raise different concerns that exist with the current process. Okay, and basically here is the summary. So here is that JP Morgan reveals, or its inventory, actually not the full inventory, as I said before. Then we cannot match clients together. We only can match clients to JP Morgan. And what happened? And here, actually, I showed you that we have these auctions where we can actually do not reveal the inventory of JP Morgan, and we can also do this multi-client X matching. And as I said, these things are going to production. Okay, thank you.
Thank you. For your dark pool thing, how many instruments are you dealing? You said you dealt with, I don't know how many orders for a time, but how many instruments is that distributed over?
You mean when you say instruments, you mean?
I mean like stocks.
Yeah, stocks.
Assets, yeah.
Yeah, so that was this 512 orders that I mentioned was for one symbol. So for different symbols, you can parallelize. So the benchmark that I gave you was for one.
So you would have to parallelize across every, so if you had 2,000 symbols, you would need 2,000 instantiations of the protocol in parallel.
Yeah, you can do this in parallel, yeah.
But it would scale, it's basically scales parallel linear with the number of instruments.
Mm-hmm, yeah.
Yeah, okay. Okay. We have some follow-up work we can send you. If you drop me a line where we actually look at real London stock market level dark market throughputs.
Oh, what do you mean real?
I mean, actually, when we modeled the throughput on the basis of there's the Plato auction mechanism, or Plato auction market, which is run by the London stock market. It's the biggest dark market in Europe. So we took their throughputs needed and managed to match those.
Is it like a star topology network, or you use secret sharing for 3 clients?
No, it's where clients are coming in. So for example, you've got multiple, you've got thousands of traders trading on Plato. So you can't, yeah. So anyway, but we'll send it, if you send me an email, we can send it to you.
Okay, yeah. Cool. I will want to see if the traders, for example, talk to each other, yeah.
Yeah, they don't, yeah, they don't.